to session 3 of real analysis. In the last session, we had discussed the principle of mathematical induction and well ordering property, and now we look more onto the set of all natural numbers, how the subsets of the set of all natural numbers would look like, and so on in this session. The first definition is that of finite sets. So, the empty set, as we all know, has 0 elements, and a set S, subset of the set of all natural numbers, is said to have n number of elements if there exists a bijection, that is a 1-1 and onto mapping from the subset n, which is equal to 1, 2, etc. up to n onto the set S. Say for example, we can see the set A equal to the set of all A, E, I, O, U, the set of all vowels, is said to have 5 elements because we can have a 1-1 and onto mapping from the subset set 1, 2, 3, 4, 5 onto A, E, I, O, U. It can be any 1-1 and onto function that we can define. For simplicity, we can take this mapping. It is definitely a 1-1 and onto function. So, such type of sets are said to have n number of elements if there is a bijection from n onto that set S. So, the definition of a finite set goes like this: a set S, subset of the set of all natural numbers, or any set S, is said to be finite if it is either empty or it has n number of elements for some n element of the set of all natural numbers. If it is not finite, then the set is said to be infinite. Now, we have the uniqueness theorem. The number of elements in a finite set will be always unique. That is because of the bijection that we have defined from n onto the set S, and so since there is a bijection from n, the set of all 1, 2, etc. up to n, that number cannot be changed. The number n will be a unique number. The set of all natural numbers is an infinite set because we cannot have a bijection from a subset, a finite subset n onto the set of all natural numbers. It is quite obvious result, and so the set of all natural numbers n is an infinite set. Now, we have another theorem. If A is a set with m number of elements and B is a set with n number of elements, and if they are disjoint, that means they do not have any element in common, then A union B is a set having m plus n elements. So, the number of elements get added up. Another result in this same theorem is that if A is a set with m number of elements and C is any subset of A with only one element, then A minus C, that means the difference of the set A from C, is a set with m minus 1 elements, and if A is an infinite subset and B is a finite set, then A difference B will be an infinite set. So, we shall look into the proof of these. The first proof is that the set A is with m elements and B is with n elements, and A intersection B is null set, then A union B has m plus n elements. So, A is given to be a set with m number of elements, and so we can have a bijection as we have seen in the definition. There is a bijection, say F, from the set of all 1, 2, 3, etc. up to m onto the set A, and therefore, the set of elements in A can be arranged as say A1, A2, A3, etc. AM. So, it is 1 to A1, 2 to A2 and m to AM. Similarly, there is a bijection G from, this bijection is what is denoted by F. Similarly, there is a bijection G from N onto B. So, we can define a bijection 1, 2, etc. up to N onto the set B, B1, B2, etc. up to Bn. So, there is this bijection as well. Let us call that bijection say G. So, now we have two bijections, one from Nm onto A and the next bijection is from Nn onto B. Using these two bijections, we shall define a new bijection or a new function say H from the set of all elements 1, 2, etc. up to M, then M plus 1, M plus 2, etc. up to M plus N onto the union of A and B, A union B, that is A1, A2, etc. AM, B1, B2, etc. up to Bn. Now, how will we define such a function H? We can see that the first mapping 1, 2, etc. up to M and A1, A2, etc. up to AM can be the same as the function F, because we are going to define a new bijection if possible from this set onto A union B, and already we know that there is such a bijection from Nm onto A. And so, using this bijection F, we are going to define a new bijection H. So, we have 1 is mapped to A1, 2 is mapped to A2, etc. M is mapped to AM. So, the same function F we are retaining there up to M. Then, after M, we have M plus 1, M plus 2, etc. up to M plus N, which are to be mapped to B1, B2, etc. up to Bn. But we have this function G mapping 1, 2, etc. up to N to B1, B2, etc. up to Bn. So, using this, how we can rewrite H in terms of G? We can take H of I is equal to same as F of I for I equal to 1 to M, and from M plus 1 up to M plus N, we need H of I is equal to G of I minus M. Then only we will be having H of M plus 1 is equal to G of 1. H of M plus 2 is equal to G of 2. So, what we require is from I is equal to M plus 1 to M plus N, we require G of I minus M. So, using these two functions, we can define a new function H so that M plus 1 is mapped to B1 and M plus N is mapped to Bn. Now, we can see none of the elements in A union B is left out. So, it is a surjection and each element has got exactly one image, and so it is an injection mapping, 1-1 mapping also. So, it is both an injection as well as a surjection, and hence it is a bijection. So, that completes the proof of the first statement, that is, we have defined a new function H as H of I is equal to F of I for I is equal to 1 to etc. up to M, and H of I is equal to G of I minus M for I is equal to M plus 1 etc. up to M plus N, and clearly H is a bijection. So, that completes the proof of the first statement. Then we have, if A is a set with M elements, I will write cardinality of A as this expression. Suppose cardinality of A, number of elements in A is equal to say M. C is a subset of A with cardinality of C as 1. Then we have to find the cardinality of A minus C. That is our problem. We have to find the cardinality of A minus C. So, we know since C is a subset of A, we have the Venn diagram something like this. We have the set A here, we have the set C which is a singleton element as this small c. So, what is A difference C or what is A? A is nothing but A difference C union C. That is, from set theory we know this result, A difference C union C gives A, and A difference C intersection C is equal to empty. Intersection C is equal to null set. Therefore, applying the first part of the theorem, we have cardinality of A is nothing but cardinality of A difference C plus cardinality of C, that is 1, and given cardinality of A is M, therefore, M equal to cardinality of A difference C plus 1, and therefore, cardinality of A difference C is M minus 1. So, that completes the second part. Similarly, we can show that if A is an infinite set and B is a finite set, A difference B should be an infinite set only, because if A difference B is also a finite set, A difference B union B will also be a finite set, and that is a contradiction to the given statement. So, that completes the proof of the theorem. Now, we have another problem in which we are given two sets, one with cardinality M and the other with cardinality N, where M is given to be less than or equal to N. How many injections can be defined from such a set A to such a set B? That means, from a set with cardinality M to a set with cardinality N, where M is less than or equal to N. So, we are going to define injections or 1-1 mappings, and so 1-1 mappings means we can see through a picture. We are given a set A and a set B. This set A has A1, A2, etc. up to AM as the elements, whereas B1, B2, etc. up to Bm, then Bm plus 1, etc. up to Bn as the elements, because we have taken M to be less than or equal to N. Now, we need to find the number of injections. So, 1-1 mappings. So, when you have A1, corresponding choices of B is, we can choose any one of these B elements for the image of A1. So, f of A1 can be any one of these n elements here. So, having the n elements taken apart, A2 has one of the n elements is being taken as the image of A1. Then for the image of A2, how many elements are remaining? Only n minus 1 elements are remaining, because 1 has been already taken as an image of A1. Then for A3, n minus 2 choices are there. So, likewise we can proceed and we can see that for A1 there are n choices for f of A1, for A2 there are n minus 1 choices, and so on. There are n minus of m minus 1 choices for f of Am. So, altogether the number of injections from the set A to the set B is n into n minus 1 etc. up to n minus of m minus 1, that is n c m choices. So, there are n c m different injections from the set A to the set B. Now, there is a problem given, find the number of injections from the set S is equal to set 1 2 to the set T is equal to set A B C. So, just now we have seen from AM or A with cardinality M to B with cardinality N, we have NCM choices of injections. So, here there are 3 C2 choices, because the cardinality of T is 3 and cardinality of S is 2. So, there are 3 C2 choices of injections from the set S to set T. Now, to find the surjections, to find the number of surjections from the set T equal to set ABC onto the set S is equal to set 1, 2, we have an equation. The number of surjections from a set S, or a number of surjections from a set A with cardinality N onto a set S with cardinality 2 is given by 2 power n minus 2. So, that is a formula given for the number of surjections from a set of n elements onto a set of 2 elements. So, using that formula, we will be getting here cardinality of T is equal to 3 and cardinality of S is equal to 2. And so, n is equal to 3, and therefore, the number of surjections from T onto S is 2 cube minus 2, which is 8 minus 2, which is equal to 6. Now, we have another set. We can prove that a non-empty set T1 is finite if and only if there is a bijection from T1 onto another finite set T2. Say for example, we can prove that result given that T2 is finite. So, the number of elements of T2 is some n, and therefore, we have a bijection say f from Nn onto T2. Now, what we are asked to prove is, we are asked to show that the non-empty set T1 is finite if and only if there is a bijection from T1 onto T2. So, we are going to prove that suppose T1 is finite, then we are going to prove that there is a bijection from T1 onto T2 and the converse part also. So, let T1 is finite, then by definition of finite sets, there is a bijection say G from Nm onto T1. So, since it is a bijection, we need T1 and T2 to be the same number of, say having the same cardinality. That means, the number of elements of T1 and T2 should be exactly the same. Otherwise, what will happen? It will not be a 1, 1 and onto mapping, it will not be a bijection. So, we have to define from Nn itself, Nn onto T1. Now, we need to prove that there exists a bijection from from T1 onto T2. There is a bijection from T1 onto T2, and which will be that bijection? You have to take the composition of the two functions. So, you can take f composition G inverse to be a bijection from T1 onto T2, or you can take G composition f inverse as well. Okay, because we need the domain and range of the two functions should be the same. So, you can take accordingly a composition, and we can show that there exists a bijection from T1 onto T2, and the converse is just the reverse of this. We can simply retract. Now, the next theorem is that suppose T and S are two sets with T subset of S. If S is a finite set, then T is a finite set. If T is an infinite set, then S is an infinite set. So, from the statement of the theorem itself, we can see that the first and second statements are exactly the same, because one is P implies Q and the other is negation Q implies negation P. So, we need to prove only one part. So, the proof is quite simple. Suppose that S is a finite set, then we have to prove that T is a finite set. So, by the definition of finite, there can be two options, either S is infinite, either S is empty set, or it has a bijection from some Nn onto the set S. Now, given that T is a subset of S, so first our assumption is if T is equal to null set is a subset of every set. So, if T is a null set, then T is obviously finite, there is nothing to prove. So, suppose that T is not equal to null set, then we can prove by the induction on the cardinality of S. If the cardinality of S is equal to 1, then the only non-empty subset of S is S itself, because the cardinality of S is equal to 1 means S has got only one element, and so the non-empty subset of S means it is the singleton set, which is the same set S itself. So, T will be coinciding with S, and so T is a finite set, we have proved. Now, if the cardinality of S is equal to K, suppose that by induction hypothesis we assume that every non-empty subset of S is finite, that is our induction hypothesis. So, we take the cardinality of S is equal to K plus 1, then we have a bijection from Nk plus 1 onto S. So, if T is a subset of S, we have two options for T, either f of k plus 1 belongs to T or does not belong to T. If f of k plus 1 does not belong to T, T is a subset of S minus f of k plus 1. So, what is the cardinality of S minus f of k plus 1? We have removed one element from S which was of cardinality k plus 1, and now the cardinality of S minus f of k plus 1 becomes k, and T is a subset of this, means by the induction hypothesis T becomes finite. So, we assume that f of k plus 1 belongs to T. Then what happens? We have a new set T1 which is equal to T minus f of k plus 1, which is a subset of S is equal to S minus f of k plus 1. Now, this has got only k elements, and so by induction hypothesis T1 is a finite set. So, if T1 is a finite set, what if we include one more element to T1? Again it remains a finite set, and therefore T becomes a finite set. And as I have told you, T is an infinite set, then S is an infinite set is just the negation of that. Now, the last section says if the set S has n elements, then the power set has 2 power n elements. This can be easily proved using the principle of mathematical induction. We have to consider the 3 cases of induction. We have to consider a single element for n equal to 1, write down which are the 2 subsets, the empty set and the set itself. It becomes, the power set becomes of cardinality, becomes a set of cardinality 2, and hence we have P of 1 is true. Then suppose that P of k is true, that means if a set has k elements, the power set has 2 power k elements. Consider a set S with k plus 1 elements, remove one element from that set, we will be getting a set with k elements for which the power set has 2 power k elements, and take the combination of that particular element which was left out with all these remaining subsets. We will be getting new subsets which are twice the number of subsets as the set of all elements with k. So, that we can do, we will be getting the power set of S has 2 power k plus 1 elements then. So, we can see that if a set S is a finite set, then the power set also has a finite number of elements. So, with that we have covered a small portion of finite sets. Thank you.